All right, let's talk about the secret sauce behind almost all modern AI search. We're going to pull back the curtain on an algorithm called HNSW. It is the powerhouse that makes lightning-fast similarity search possible, in your photo app, in chatbots, pretty much everywhere. So let's get right into it. I mean, really think about that for a second. How on earth can your phone sift through thousands of photos to find every single picture of your dog? Or how does a music app recommend a song that just feels right, that has the same vibe? It feels a little bit like magic, doesn't it? Well, it's not magic. And that's the key idea we're going to explore today. At its core, HNSW builds something like a super efficient GPS for all your data. It lets an AI navigate a huge, messy library of information at frankly unbelievable speeds. So hang on to that map idea, because it is absolutely central to understanding how this whole thing works. So why do we even need this special map in the first place? Well, that gets us to the fundamental problem with AI search. It is a totally different beast compared to the kind of search we're used to, like on a traditional search engine. See, a classic database is fantastic at finding an exact keyword, right? You search for cat, you get results with the word cat. Easy. But an AI needs to find things that are conceptually similar, other images that look like a cat, or maybe a piece of text that has the same meaning as the word cat. Trying to find similarity in what we call high-dimensional vector data is just an incredibly hard, computationally expensive problem to solve. And this is exactly where HNSW comes into the picture. It gives us a really elegant solution to this whole similarity search problem by creating that smart map we were just talking about. Okay, let's get the technical definition out of the way. It sounds like a real mouthful, but stick with me. Hierarchical just means it has layers. Navigable small world is a fancy way of saying it's super easy to get from any one point to any other in just a few hops. And the key word here is approximate. That's the secret to its speed. It doesn't need the one perfect match, just one that's close enough, and it can find it incredibly fast. And this right here is just a perfect way to picture it. The top layers of this HNSW graph are like the interstate highways. They let the search algorithm make these huge jumps across the data to get into the right general neighborhood really, really quickly. Then the bottom layers, those are the local streets, letting it zero in on the exact spot to find a super precise match. So we have this awesome multi-layered map. How does a search actually navigate through it? Well, the process itself is a really clever step-by-step journey, basically from the top all the way down to the bottom. The process is actually pretty slick. It all starts at the very top, on that express lane. From there, it does what's called a greedy search, which just means it finds the closest point on that layer to what you're looking for. Then, from that new spot, it drops down to the next layer, and it just repeats this process over and over. Find the closest neighbor, drop down a layer, until it hits the very bottom, the local roads, where all the actual data lives. And one of the coolest parts is that this whole system is highly tunable. It's like having a bunch of dials you can turn. Developers can adjust these key parameters to find the perfect balance for whatever they're building. If you need more accuracy, you can increase the number of connections between points. Need more speed? You can dial them back. It's this constant dance between performance, accuracy, and how much memory you're using. And that trade-off, that brings us right to the practical dilemma every single engineer faces when they use HNSW. This constant battle between its incredible, blazing speed and its very real cost. I mean, the advantages are huge. You can't deny it. The search speed is what tech folks call logarithmic, which basically means that the search time barely goes up even if you dump millions of new data points into it. It scales beautifully. And unlike some other methods, you can add and remove data on the fly without having to rebuild the entire map from scratch. But here is the catch, and it's a big one. To get that amazing speed, the entire map, the whole graph, and all the data has to live in your computer's RAM. And as anybody who's ever built a computer knows, RAM is expensive. This high memory requirement is the single biggest trade-off, and it leads directly to higher server and infrastructure costs. So, knowing that, how has the industry decided to actually implement this super powerful but kind of pricey algorithm? Well, that brings us to the real-world database showdown, looking at how the landscape is shaping up for 2026. The main event, really, is a battle between two different philosophies. On one side, you've got solutions like pgvector, which integrate HNSW right into a database people already use, like Postgres. On the other side, you have these specialized cloud-native services like Pinecone, which were built from the ground up to do nothing but vector search. And wow, recent benchmarks are pretty striking. In a direct comparison, the integrated solution, pgvector, showed a staggering 16 times higher query throughput. That means it can handle 16 times more searches every single second. That is a massive performance gap. And it's not just about handling more queries in total, it's about how fast each individual search is. Those same benchmarks showed pgvector spitting out results with 28 times lower latency. For a user, that's the difference between an instant result and a noticeable delay. And this all loops back to that cost problem we talked about. By using existing infrastructure and open source tools and avoiding paying a premium for managed RAM, teams that host pgvector themselves are seeing typical cost savings of around 79% compared to paying for a specialized service to do a similar job. That's huge. So this table really lays out the whole landscape for us. You can see pgvector is kind of a no-brainer if you're already using PostgreSQL and you want to mix your vector search with traditional data, all while keeping costs way down. Pinecone, on the other hand, it really shines when you need to scale to billions of vectors and just want a hands-off, managed service, but you're going to pay for it. And then you've got MongoDB Atlas, which kind of finds its sweet spot for teams that are already deep in that document-based ecosystem. So how do you choose? Well, it really boils down to a few simple questions. Are you already on Postgres? Then pgvector is almost certainly your best bet. Are you dealing with a truly massive scale, like billions of items? Okay, then you should probably consider a specialized service like Pinecone. And if your app absolutely cannot tolerate any delay, where every millisecond counts, then you'll want to evaluate a specialist like Pinecone or maybe Qdron. And that really leaves us with the big question for the future. The core technology, HNSW, is pretty much set, but the real race now is to see which philosophy for deploying it is going to win out in the end. Will it be the deep, cost-effective integration of open-source tools into the databases we already have, or will it be the simple, massive scale offered by these specialized managed services? The answer to that is really going to shape what the next generation of AI applications looks like.